All right. Hi, everyone, and welcome to the AutoML Speaker Series. I'm really excited to introduce Roger Grosse, who is an assistant professor of computer science at the University of Toronto and a founding member of the Vector Institute. Roger received his PhD in computer science from MIT and then spent 2 years as a postdoc at the University of Toronto. He holds a Canada Research Chair in Probabilistic Inference and Deep Learning, an Ontario MRIS Early Researcher Award, and a CIFAR Canadian AI Chair. I'm in general a huge fan of Roger's work, but I'm particularly excited by his work on self-tuning network, which he's going to present today. Lucky coincidence. As a reminder, Roger will be around during the talk to answer questions. During the talk, I will also be clustering and aggregating questions to take to our live Q&A at the end. So without any further ado, let's see Roger's talk.
I'm Roger Grosse, and I'll be talking about self-tuning networks, a way of amortizing the hypergradient computation for hyperparameter optimization. This talk will be based on 2 published papers. The first one is self-tuning networks, bilevel optimization of hyperparameters using structured best response functions. This was primarily the work of 3 students, Matt Mackay, Paul Vicol, and John Lorraine, also in collaboration with David Duveneau. And the second paper is Delta STN, efficient bilevel optimization of neural networks using structured response Jacobians. This is primarily the work of my student Juhan Bey, and this is published at NeurIPS 2020. So I'll begin by observing that a lot of problems that we're interested in solving in machine learning, especially hyperparameter optimization, have a bilevel structure, in the sense that there is an optimization objective, the outer objective, which is itself defined in terms of the optimal solution to an inner objective. So in the context of hyperparameter optimization, the inner optimization problem, the one shown on the right, would be to optimize the weights of a neural network to minimize the regularized training error. The outer objective, shown on the left, would be to find the hyperparameters which minimize the validation error of the optimal weights as far as the inner objective. So this is an example of a bilevel optimization problem, and there are various techniques for solving them, which I'll summarize later, but a lot of them require the gradient of the outer objective. This is what I'll refer to in this talk as the hypergradient. This is what we need if we want to do any sort of gradient-based optimization of the outer objective. And computing this hypergradient is a big computational challenge required for many different types of machine learning algorithms, even outside bilevel optimization. And so computing this hypergradient will be the focus of this talk. So one way to approach bilevel optimization problems is not to use gradients at all and just treat them as a black box optimization problem. So if you're tuning hyperparameters, probably the vanilla ways of doing that would be with grid search or random search, where you just try a bunch of values and train networks for each one and pick the one that does the best on the validation set. These are non-adaptive approaches, so they don't make use of information that you've learned from previous queries. A somewhat smarter way of doing the black box optimization is using an adaptive method such as Bayesian optimization. So this actually tries to use information learned from previous queries in order to choose points that are both likely to perform well, but also provide useful information about the cost function. So Bayesian optimization is great. It's been a key enabler of many applications such as AlphaGo, but it has some drawbacks. So one drawback is that, like other black box optimizers, it doesn't exploit gradient information, at least not the commonly used versions of the algorithm. And the other drawback is that it's an offline procedure, which means it requires training the algorithm many times, typically from scratch. So we can often do better if we make use of gradient-based optimization. And in order to do that, we need to compute the hypergradient. And there are actually a great many different applications in machine learning that somehow make use of the hypergradient. So the canonical one that I'll be using as the running example throughout the talk is gradient-based hyperparameter optimization. But there are many other cases that we might not even consider bilevel optimization, such as influence functions used to figure out which training examples are useful or relevant to a particular prediction. And neural net architectures based on implicit layers and deep equilibrium models and cases like that. So there are many different cases where we would like to have a hypergradient. And so hypergradients, as I'll describe in a moment, are impractical to compute exactly. And so in almost any paper that you see that uses hypergradients, they're almost always computed using one of two methods. The first one is implicit differentiation. So you can apply the implicit function theorem to get an expression for the hypergradient, but this expression involves a very large linear system. You have to solve a linear system involving the Hessian of a neural net or some matrix that's closely related to it. And this is typically done using an iterative procedure, something like conjugate gradient, Neumann iterations, or the Lisa algorithm. So that's one way you can do it. Another way is to unroll the inner optimization. So that gives you a differentiable procedure that you can backprop through in order to get the derivative with respect to the hyperparameters. And so these are the two methods that are almost always used to solve the problem. And they both have the disadvantage that they both require expensive iterative computations each time you want to update the outer variables. And so the goal of this talk will be to present a third alternative that you can consider for hypergradient computation. And the way that this alternative will differ from the other two is that we amortize the hypergradient computation by learning a hypernetwork. So you invest some computation into learning the hypernetwork, and then the individual gradient computations for the outer objective should be fairly cheap. And this will allow you to adapt hyperparameters online as the neural network is training. And so the procedure I'll define will turn out to have only a small constant factor overhead compared with training a single network. So it will require about twice the amount of memory to store the parameters as the elementary neural network, and require a small constant factor the amount of compute time to train the network. And so I've described a high-level umbrella picture of the different places that hypergradients are used. But now, in order to make things a bit more tractable, I'm going to limit the scope. So the first way I'll limit the scope is that we are dealing with neural networks. So I'll talk about a way of approaching the hypergradient computation that exploits the structure of neural networks. A second limitation is that I'll be focusing on outer optimization variables or hyperparameters that appear as part of the inner objective. So this would include things like regularization hyperparameters, such as dropout or data augmentation rates, but it rules out dynamical hyperparameters, which aren't part of the training objective, but influence maybe the efficiency of training. So things like learning rates and momentum hyperparameters and things like that. So we're not considering those for now. And this also has the implication that for hyperparameters like dropout, they've been shown to have both explicit and implicit regularization effects. They have explicit regularization effects insofar as they change the cost function that is being optimized. And they also have implicit regularization effects insofar as they change the amount of gradient noise. And so in this talk, I'll only be considering the first effect and not the second. And so we might find suboptimal hyperparameters to the extent that we're not accounting for implicit regularization. And accounting for the implicit regularization is still a very hard problem. I'll narrow it down in another way, which is that we consider only a single inner objective that's being optimized. So we're trying to train one neural net using one training loss. So this rules out certain types of bilevel optimizations, such as implicit layers of neural nets, where you have a different inner objective for each data point that you visit. And finally, we're going to limit the scope to relatively small numbers of outer variables. So optimizing perhaps dozens of hyperparameters rather than millions of hyperparameters, as some other papers have attempted to do. So these are the limitations that I'm putting on the method, and broadly categorize approaches to bilevel optimization on 2 dimensions. So I've already distinguished black box versus gradient-based optimization. Do we use the gradient information or not? And we can also distinguish offline and online optimization, right? Do we use an offline procedure that requires many runs of the inner optimization in order to solve the problem? Or do we want an online procedure that can be done online in one training run so that you can solve the bilevel problem in a comparable amount of time to just training a single network? And so our approach, the self-tuning networks, will be in the bottom right quadrant. It's a gradient-based approach to online hyperparameter adaptation. So I'd like to contrast the bilevel optimization setting with another setting that's commonly used in deep learning, which is simultaneous optimization. This is something that's been very successfully used for things like GANs and neural architecture search. Here you have 2 different neural networks, or 2 different sets of parameters that are being simultaneously optimized to 2 different cost functions. And in this setting, the aim is to find a Nash equilibrium where each of the 2 players thinks that its solution is optimal for its own cost function without thinking about how the other player will react to it. But I claim that this is the wrong solution concept for hyperparameter optimization. And the reason is that it only takes into account, when you're optimizing the outer parameters, it only takes into account their direct effect on the outer objective, the validation loss. So in the case of hyperparameter optimization, if you consider a hyperparameter like a dropout rate, this doesn't appear directly in the validation objective because dropout isn't used at test time. And so the direct gradient of the validation loss with respect to the dropout rate will actually be 0. And so we have no way to optimize that hyperparameter with simultaneous optimization. And even in the setting where the gradient is non-zero, this simultaneous optimization setting will ignore some effects that we might care about. So for instance, if you're doing neural architecture search and the outer optimization variables somehow parameterize the network architecture, the simultaneous setting might be able to make a trade-off between the performance of the network, assuming the current weights, versus the computation time. But it won't consider the regularization effect of having a more constrained architecture, right? Having fewer units per layer might encourage the network to learn a more efficient representation. So I claim that what we actually want for settings like hyperparameter optimization is a Stackelberg equilibrium. So this is the game solution where the outer player goes first and considers how the inner player will react to its choice. Right? When we're tuning the hyperparameters, we want to think about how the weights of the network will react to the hyperparameter choices. And so a key concept in thinking about bilevel optimization is the best response function. This is the function mapping from the outer variables. I'll be using the hyperparameters as the running example. So it's the function mapping from the outer variables to the optimal inner variables for the inner objective. And so I will write that as the function R of lambda, which is just the argmin of the training loss with respect to W. And so if we somehow had access to the best response function, then we could do gradient-based optimization over the hyperparameters because we can simply write the validation loss in terms of the best response function. And so what we're showing on the right is an example of the inner objective defined as a function of both W and lambda, and the best response function is shown with the solid green line. Okay, so if we want to do gradient-based optimization of the outer objective, we're going to need to compute the total gradient of the validation loss with respect to our hyperparameters. And so when we apply the chain rule, we get a sum of two different terms. The first term is the direct gradient. This says how perturbing the hyperparameters will directly affect the validation loss. Right? You write down the formula for the validation loss and compute the partial derivatives of that with respect to the hyperparameters. So this is the term that's being considered in the simultaneous optimization setting. The second term is the response gradient. So this determines how changing the hyperparameters changes the validation loss insofar as it changes the optimal solution to the inner objective. So this is the thing that we really care about when we're optimizing the hyperparameters. And so if we look at the formula for this, this can be rewritten using the chain rule as the response Jacobian times the derivative of the validation loss with respect to the weights. The response Jacobian says how the optimal weights change if you perturb the hyperparameters. So we have a formula for the response Jacobian at the bottom of this slide. And unfortunately, this formula involves the inverse of the Hessian for the neural network, the Hessian of the training objective. And unfortunately, this makes it impractical to compute because the Hessian is a gigantic matrix. The dimension is the number of parameters of the neural network, which could easily be in the millions or billions or perhaps even trillions. And so approximating this linear system is a significant challenge. Visually, we can understand the response Jacobian by taking the first order Taylor approximation to the best response function. So that's shown as the dashed green line. Okay, so how do we actually approximate this hypergradient? So I'll be talking about the main technical contribution for this talk, which is self-tuning networks. And so the idea behind this approach is that at any given time, we're going to have a guess lambda of the optimal hyperparameters. And what we'd like to do is train a hypernetwork to approximate the best response function accurately in the vicinity of these hyperparameters. And if we have that, then we can cheaply approximate the response Jacobian just by differentiating through our hypernetwork. That can be done with ordinary backprop. This is exactly what we need to compute the hypergradient. And if we have already gone through the work of learning this hypernetwork, then it actually makes the hypergradient computation very cheap. Instead of doing an expensive iterative procedure to solve a large linear system, we can just do backprop through an ordinary neural network. All right, but how do we actually learn this hypernetwork? And so the basic idea, which was already pioneered by a paper by John Lorraine and David Duveneau in 2018, is basically to train your hypernetwork like an ordinary neural network. So for each batch of data, you sample a new vector of hyperparameters, and the hypernetwork predicts a weight vector, perhaps conditioned on those hyperparameters. And you do a gradient update on the hypernetwork in order to reduce the regularized training loss on that batch. And so it's basically computing the things that an ordinary neural net would, except that it can perhaps perturb the weights of the network in order to account for the changes to the hyperparameters. So conceptually, this sounds pretty good, but this leaves the big question of how do we compactly approximate this best response function, right? This is the mapping from hyperparameters to the weights of the elementary network. This is a really complicated, high-dimensional nonlinear mapping. And in fact, the output dimension of this mapping is d, the number of weights of the elementary network. So you can imagine it being really hard to represent such a function. So there's a partial solution. We can restrict the hypernetwork to be linear. Have a formula for the linear hypernetwork. It's just a linear function of lambda. Why can we get away with this? Well, the idea is that the only thing we need the hypernetwork for is to compute the response Jacobian. And the response Jacobian is a linearization to begin with. And so perhaps a linear architecture is sufficient to compute it. And so this argument is sort of true. It has some subtleties that I'll get into later on in the talk. But I think linear hypernetworks seem to be fairly effective. But unfortunately, this doesn't solve the problem because the dimensionality of the hypernetwork is still huge. To represent a general linear function from hyperparameters to the weights of a network, this will require d times h parameters, where h is the number of hyperparameters. So this is still too large to practically represent. And so I'll start with another observation, which is that best response functions can actually have a very particular structure that we can exploit. And so consider, for instance, the problem of linear regression with an L2 regularizer. So here we have the formula for a linear regression objective, and we're penalizing the L2 norm of the Jacobian of the prediction function, equivalent to the L2 norm of the regression weights. And that penalty is scaled by the exp of the hyperparameter lambda. And it's actually possible to derive an optimal solution. We can derive an explicit form for the best response function in terms of lambda. And so the optimal weights can be written as a product of a matrix Q times a vector S. And the matrix Q can be written as a fixed matrix, which is each row of this matrix is multiplied by a value that depends on the hyperparameters. So it's a fairly simple equation that exactly captures the best response function globally. And the interesting thing about this is that the only effect of the hyperparameters is to rescale the individual features. In this case, the features come from the principal components. So if we interpret that solution as a neural network, it looks something like this. So we have a linear neural network, takes in an input x and produces a scalar output y, and it consists of two linear layers. The first does a matrix vector multiplication by the matrix Q0, and the second layer does a vector-vector multiplication to produce the output y. And the activations in the first layer are modulated based on the hyperparameters lambda. So we have modulatory connections which multiply each of the activations by values that depend on lambda. And so the intuition here is that the hypernetwork reacts to the hyperparameter by emphasizing or de-emphasizing different features. So if it sees a large value of the regularization parameter, it has the capability to de-emphasize a certain feature. So I think this is a generally useful architecture for representing hypernetworks. And so our self-tuning network architecture combines both of the aforementioned architectural insights. So we make the hypernetwork linear in lambda. The weights are linear as a function of the hyperparameters. Now this isn't a linear network. It's not linear in the inputs. It's linear in the hyperparameters. So we combine that insight with that of modulatory connections. And so each weight layer implements the simple functional form, which is closely inspired by the optimal solution for linear regression. So we have the ordinary neural network computations, except that the weights are, the incoming weights to each unit are rescaled by a value that depends on the hyperparameters. And so if you count the parameters in computations, the number of parameters is little more than twice that of the elementary network, because we have two copies of the weight matrices instead of one. And the computational cost is slightly more than the elementary network. We have to do a little bit of work to manipulate matrices that are the size of the parameter matrices, but the actual feed-forward computations done by the network, so if it's a convolution network, the number of convolutions and things like that, that's the same as ordinary training. So the amount of computational overhead is actually fairly minimal. Okay, so how do we train the hypernetwork? So let's first imagine that the hyperparameters lambda are fixed, rather the distribution of hyperparameters is fixed, and we want to train the hypernetwork. So the hypernetwork's training objective is just the regularized training loss. So it's the expectation of the regularized training loss with respect to the hyperparameter distribution. So for each batch, it receives a hyperparameter vector, it outputs the weights of the network, and then it's evaluated on the regularized training loss with those weights. And so we simply do ordinary gradient descent and ordinary backprop to update the hypernetwork. Okay, so that's the hypernetwork, and we've assumed so far that the hyperparameters lambda are fixed. But how do we actually adapt lambda? And remember that we're sampling the hyperparameters from a distribution for each batch of data, and so assuming a Gaussian distribution, we also have to choose the scale of that distribution, right? How large a perturbation do we apply to the hyperparameters for each batch? And so when we adapt the hyperparameters, we have two different goals. There's the ultimate goal of this training, which is that we would like a hyperparameter vector that leads to good validation loss at the end of the day. But we also have to worry about how this distribution affects the training of the hypernetwork. So we would like to choose values of lambda and sigma that give a useful distribution for updating our hypernetwork. And so what we do is we adapt lambda and sigma simultaneously to updating the hypernetwork. We adapt lambda to minimize the expected validation loss. And we essentially do that by differentiating through the hypernetwork. And so we're implicitly making use of the response Jacobian. So choosing the perturbation scale sigma is a little bit more subtle. Right? We want to choose a perturbation scale that is broad enough to give information about the response Jacobian, but not so broad that it becomes impossible to represent the hypernetwork with a linear function. So in the left-hand figure, we have an example where the distribution is too narrow and the hypernetwork can minimize its objective without capturing the Jacobian. In the right-hand figure, we have an example where the perturbation scale is too large, and so the hypernetwork has to fit a region that is too large to be modeled with a linear function. But if we choose an intermediate value of the perturbation scale, like on the middle figure, then we can get a good estimate of the response Jacobian. And so how do we adapt this scale? If we simply adapted it to minimize the validation loss, like we did for lambda, then the optimal value would be 0, because there's no advantage in terms of validation loss to making things stochastic. And so in order to encourage a broad perturbation distribution, we regularize the entropy of the distribution. Right? We encourage the distribution to have high entropy, which encourages large perturbations. But at a certain point, the perturbations will be pushed to be smaller because they'll start to interfere too much with the validation loss. And so the algorithm essentially trains all three of these sets of parameters jointly, the hypernetwork, the hyperparameter lambda, and the perturbation scale sigma. And so everything is essentially trained as a simultaneous game. And so how does this work? So here we have an example of adapting the dropout parameter for RNN language model on Penn Tree Bank. And we see over the course of training that the dropout rates tend to start out small and get larger. And this isn't just an effect of the adaptation taking a long time to converge, because the left-hand figure shows the whole process starting from 5 radically different initializations going all the way from 0.05 up to 0.9. And we see that regardless of the starting value, the initialization is unlearned very quickly, and all of these training runs quickly follow the same schedule. And what we find is that this schedule actually works better at the end of the day than any fixed hyperparameter setting. So if we compare it to a grid search of the same architecture trained with individual dropout rates, the STN can beat all of them. And it's not just an effect of the STN dynamics. This is actually apparently a good dropout schedule, because using the dropout schedule to train a network outside the context of STNs also beats all of the individual settings. Here we have some examples of training convolutional networks for image classification on CIFAR 10, and we're adapting 15 hyperparameters that include layer-specific dropout rates, including all the layers of the network plus the input layer, obtaining the amount of input noise, various kinds of data augmentation. And we see that the hyperparameters adapt in very different ways. It tends to choose a large dropout rate for the very top layer of the network, a standard trick in training convnets. It turns off dropout in a lot of other layers completely. And at the bottom of this slide, we're comparing the validation loss achieved in a certain amount of time for STN versus other kinds of hyperparameter optimization, grid search, random search, and Bayesian optimization. And the fact that everything is optimized in a single training run means that the STN is able to find a competitive hyperparameter setting much faster than any of these other methods. Okay, so that was the original self-tuning network architecture. And now we want to tell you about some improvements that we've made to it. And this is the work of Juhan Bey, presented at NeurIPS 2020. So our delta STN is the result of some algorithmic improvements that we made to the basic STN approach. So the two improvements are a centered parameterization of the hypernetwork and a linearization of the network computations. And I'll describe in a bit what problems these are solving and why they help. And so what we find is that the delta STN significantly improves the speed and stability compared with the original STN. And in this presentation, I'm going to describe the improvements using a full linear hypernetwork just to keep the notation simple. But in practice, we actually apply these techniques to a compact architecture based on the original STN. So still low overhead compared with training the original network. Okay, so the first trick is to use a centered parameterization of the hypernetwork. So on the left-hand side, we have a full linear hypernetwork, which I use to motivate the STN architecture. On the right-hand side, we have the centered parameterization of the same network. And these are essentially, they're equivalent in terms of the representational power. They can all represent general linear functions. But the difference is that the hyperparameters are centered by subtracting out the mean value lambda 0. And this centering results in a nice intuitive separation between the two different parts of the hypernetwork. We have the intercept term W0, which you can think of as the current weights of the network. Right? These are what the algorithm thinks are the optimal weights for the current set of hyperparameters. The other set of hyperparameters is the linear part of the hypernetwork. These parameterize the response Jacobian, how the weights should change in response to a perturbation to the hyperparameters. All right, and so why are centered parameterizations useful? Well, there's one reason that a lot of you might be used to already from training neural networks, which is that centering things often improves the conditioning of a cost function. So there is a classic analysis by Jan LeCun in 1998, which you can also find in the first chapter of my neural net training dynamics course notes. You can basically understand how centering inputs or centering activations affects the conditioning of the Hessian of a cost function. And so that's a kind of standard thing in neural net optimization. And often makes maybe a subtle difference in the training, but it turns out to be really important for learning these hypernetworks. And the reason is that the uncentered representations create certain harmful game dynamics in the optimization. And so why does that happen? Well, if we think about the original STN parameterization, the uncentered one, what does the gradient look like for the Jacobian? You can actually derive the formula for it, which is the outer product of the training gradient with the current sampled hyperparameters. And what this says is that moving the hyperparameters in the direction that they're currently in has the effect of moving the parameters in the direction of the training gradient. Right? This is perhaps wrong, right? This comes, right? We want to update the weights of the network in the gradient direction, but the Jacobian is mistakenly believing that updating the hyperparameters in that direction will move the weights in the gradient direction. And this looks like a really good direction to move in, because that's the training gradient direction. Early in training, it's probably well aligned with the validation gradient. And so it thinks that it can get lower validation loss just by moving the hyperparameters in whatever is their current direction. And so here's a toy example to illustrate this phenomenon. We have a bilevel optimization problem shown on the left. The outer objective is 1/10 times lambda squared plus w, and the inner objective is w squared. And this is kind of a trivial bilevel optimization problem because the inner objective doesn't depend on lambda. So the response Jacobian is 0, and you can just solve it with simultaneous optimization of these two different objectives. They don't even have to think about each other. And if you use the centered parameterization, like we see on the right, that's actually what happens. So starting from different initializations of lambda and w, the trajectories basically converge straight to the optimum for each of the variables independently. But if you use the uncentered parameterization, then what happens is that it mistakenly puts information that should go in w into the Jacobian theta. And so the Jacobian changes along these trajectories, and having a wrong Jacobian means you have incorrect gradients for the outer objective, and so things are kind of pushed in weird directions. And I chose this example to illustrate the effect. So it's sort of constructed to amplify this effect. I don't think it's quite this strong during ordinary neural net training, but this is basically what's going on. And so just making this one change to the architecture, centering the parameterization, can actually improve the results quite a bit. So here we are adapting the L2 regularization parameter for linear regression. And if we use the original STN, we see that it initially takes a very large value before gradually going down to the optimal one. Whereas if we modify the objective by centering it, then we can eliminate this pathology and converge to something resembling the optimal parameters much faster. Okay, so that was the first trick, centering. The second trick behind the delta STN is to linearize the elementary network. Right? We want to approximate the network with the first order Taylor approximation around the current weights. Similar to things like the neural tangent kernel. So why is this a good idea? Well, the problem is that when we sample lambda, if we use a large perturbation scale, then it can be fairly difficult to approximate the best response function as linear in the support of the hyperparameter distribution. And so here we have an example of a bilevel optimization problem. So we have the hyperparameter represented on the vertical axis and two inner parameters on the horizontal axis, and the contours show the inner objective for any particular value of lambda. And so in blue, we're showing the exact best response function. The dashed blue line shows the exact best response Jacobian. That's the thing that we would like to approximate. But if you actually optimize the linear hypernetwork with a distribution of hyperparameters, you actually get what's shown in the red line. That's the optimal linear hypernetwork. And the approximate Jacobian is the slope of the red line. And so unfortunately, the slope of the red line is very different from the slope of the blue line, which means that our estimated Jacobian is fairly inaccurate. And so why does this happen? Well, if you look at the cost for the true Jacobian, shown in the dashed blue line, you can actually see it's much higher than the cost for the red line, because if you move too far from the current hyperparameters shown in the star, then it will fall far outside the contours. So it has to be very conservative in how it reacts to lambda in order in order for it not to be too nonlinear. And so why is the best response function so linear? Well, I claim that it's because the neural net's function itself is nonlinear in W. And so that nonlinearity is what causes the best response function to be nonlinear and hard to approximate. But if you think about, why do we need this hypernetwork? We need it for the Jacobian. And the Jacobian is defined infinitesimal perturbations to W. And so if we only need to consider infinitesimal perturbations, we should be able to approximate the network computations as linear. And so what we do in this approximation is we replace the network computations with their first order Taylor approximation around the current weight vector. So essentially the same approximation that leads to the neural tangent kernel. And this can be written in a shorthand that delta y equals the Jacobian times delta w. This is the origin of our term delta STN. And so what are the effects of linearizing it in this way? Well, there's the disadvantage, which is that now we're approximating the network computations. But the advantage is that now the response function for this linearized network is more linear. And so we might be able to approximate it fairly accurately with a linear hypernetwork. And so it seems that the second effect wins out, and we can actually approximate the response to Jacobian much more accurately with the linearized network. So that's one interpretation. We also derived an alternative interpretation. You can find the details in our paper. And basically, you can interpret this whole training procedure as approximating the response to Jacobian for a modified inner objective. So this inner objective is rather than the regularized training loss with the current hyperparameters, we define the modified inner objective to be the expectation of the regularized training loss with respect to the perturbed hyperparameters, right? So we want a single weight vector that is fairly robust to the choice of hyperparameter values. And so that, so the best response function for this modified inner objective is the one shown in green. And we're taking the Jacobian to that's represented as the dashed green line. This is a much better match to the exact best response Jacobian in blue. So even though we've modified the inner objective, its Jacobian seems to be a pretty good match to the original one. All right, so how well does this work? So we can evaluate these different procedures on linear regression problems where it's possible to find the exact optimal hyperparameter. And so we're comparing both the choice of L2 regularizer on top and the dropout rate on the bottom. And what we see is that the delta STN is consistently able to converge faster and get a more accurate approximation of the true optimal hyperparameter compared to the original STN. Moving beyond linear regression, we can also consider training a deep linear neural network with Jacobian norm regularization. And so deep neural networks are interesting because they're equivalent to linear regression in terms of what they can represent. And so there's a lot of analysis that we can do analytically about these networks. So for instance, we can the optimal regularization parameter for the Jacobian norm, just like we would for linear regression. But the dynamics of these networks are much more like the dynamics of ordinary nonlinear neural networks. And so we can separate out the original STN from the centered STN, basically applying the first trick I mentioned, the centering trick. And then we can distinguish that from the full delta STN that involves both the centered parameterization as well as the linearized network. And we see that the centering helps and that the linearization consistently helps further. We can compare the optimization of the validation loss on various problems. And we see that for both an MNIST MLP and a fashion MNIST CNN, that the delta SDN consistently outperforms the original SDN in terms of the speed of minimizing the validation loss. And so here we have comparisons on a variety of problems. So we're comparing both the STN and the delta STN against the baselines of random search, Bayesian optimization. And we see that the original STN pretty consistently outperforms both random search and Bayesian optimization, and that the delta STN consistently outperforms the original STN in terms of the validation loss. So to conclude, I've introduced the self-tuning network, which is another way of estimating hypergradients. So hypergradients are almost always estimated either using unrolling of the inner optimization procedure or the implicit function theorem. And so self-tuning networks are a third approach. They're based on training hypernetworks that exploit the structure of the best response function. So we can amortize the computation of the hypergradients by training the hypernetwork, and that allows us to approximate the response Jacobian very cheaply just by differentiating through the hypernetwork. So this whole thing is trained simultaneously as a simultaneous game. So the hyperparameters are adapted online as the network trains. We also introduced the delta SCN, which uses a centered parameterization and a linearized network, and this improves the speed and stability of the STN training. And so this whole thing has a very low overhead compared to just training a single network. So it requires the same amount of memory for the activations, about twice the amount of memory for the parameters, and depending on exactly how you set up training, probably about a factor of 2 or 3 overhead in terms of the running time of the procedure. And so this method is able to produce solutions competitive with Bayesian optimization in a single run of training. So I think this opens up a lot of interesting future directions. So the first one is a fairly natural extension, which is to move beyond the IAD setting of training set and validation set drawn from the same distribution. And so we can consider settings where there's a more fundamental shift, such as a change in the data distribution or some form of corruption that's only applied at validation time. I think there's also a lot of interesting algorithmic work to do to understand the game dynamics induced by the simultaneous optimization of the hypernetwork and the hyperparameters. It's a kind of simultaneous differential game, but it has perhaps a lot of additional structure specific to the hypernetwork setting. And it would be interesting to see how that can be exploited to improve the optimization performance. I mentioned earlier that in adapting the hyperparameters, we were only accounting for the explicit effects of regularizers like dropout. It'd be very interesting to see if these methods can be adapted to account for implicit regularization effects as well. And finally, I described hypernetwork architectures that were suitable for the particular case of hyperparameter optimization. But I think the general strategy that we've been taking of training hypernetworks whose structure is motivated by a particular problem, I think this can be applied more broadly to other situations where we need hypergradients, such as influence functions, neural architecture search, and related problems. So I think that this work opens up a lot of exciting directions. So thank you all for attending. I'll open it up to questions.
Okay, thank you, Roger. As I said in the beginning, I really love this work when it was just a PDF somewhere, and it was really, really great to hear about it. So I guess I will be very efficient in our usage of time because we have 5 minutes and I have a bunch of questions. So the first one is around how would this work when you have hyperparameters that affect the capacity of the network? So when you're changing the number of weights, for instance. I assume that there is a way to design an hypernetwork that works in that case, but yeah, do you want to comment on that?
Right. So I think the challenge of these architectural hyperparameters probably has to do with the discrete aspect of it. So the fact that you have a discrete number of units in the layer, so you can't literally do gradient descent on it. We think that you could use something like reinforce in those settings, and you'd still be able to make use of the hypernetwork. So you still have the kind of amortization of the response function. So it might be like slower to adapt lambda, but lambda has tended to adapt fairly quickly anyway in our experiments. I guess there's a question of how important the response Jacobian is for architectural hyperparameters, because you could treat it as a kind of simultaneous optimization problem and only use the direct term, in which case you'd basically be trading off the computational cost of running the network or some other resource metric versus the performance of the network. And I guess approaches like ENAS and DARTs and things like that use some information. So I think ENAS is simultaneous, if I remember right. But, some of these methods use some information from the response Jacobian, but it's not clear how important it is, or if it is really more like a simultaneous game. So most of the hyperparameters that we've looked at were cases where pretty much all the important information is in the response term.
Yeah, makes sense. I guess I was thinking the architecture search is one case, but another case could be when you just want to change the number of channels of a convolution, right? Do you think the response Jacobian would work well in that case, or do you think that's? I mean, because it's one of the basic hyperparameters you will want to tune.
Right. Yeah. I mean, I think the intuition for what the response Jacobian would do is say, like, if this unit is turned off, then you should adjust these other units in this way in order to capture some of the same information. And how useful that is, I don't really know, right? It might be that you just want to like order the features, and if you drop some, you just lose those features and you don't have to react to it, in which case the bilevel part wouldn't be all that important.
Right. No, that's really interesting. I guess not so related, but kind of. I knew about the work, but I was very surprised by some of the results, particularly for vision problems, where you basically showed like strong online performance. You basically don't have to train from scratch again after you find the optimal lambda star in some sense. So do you have a sense of where does that performance come from? Does it come from the schedule, so to speak? Does it come from the fact that you learn a function really? Or does it come from the optimum? So if you try and retrain just from the optimum, does that achieve the same performance or better performance?
Yeah, so in at least some of our experiments, we did retrain from the optimum, and that also performed about as well. And I don't remember which subset of the experiments we did that for. We definitely did that for the dropout schedule experiment they mentioned. So I think there are a lot of issues in the kind of path dependence that we don't really understand, because as the hyperparameters adapt, then as the network is optimizing to the current hyperparameters, it still has some memory of the previous hyperparameters. Yeah. And so there could be useful information that was learned in those that wouldn't be recovered if you started again from scratch. So they're definitely like those sorts of effects are definitely possible in principle, and understanding how this whole procedure interacts with kind of implicit regularization and norm minimization and things like that seems like a really important problem. And so it seems like, it didn't hurt us too much in practice, but we don't have a good theoretical understanding of why.
Yeah, that's great. I'm watching Tam. I mean, this is a fascinating discussion because I do think that for augmentation protocols, it could be super useful. And you do have an augmentation with hue, saturation, and brightness. Anyway, I wish we could talk about this more. I guess we'll talk more offline. I wanted to thank you so much for presenting. This, as I said, this is fascinating work. And thank you so much for sticking around and answering all the questions in the chat as well. There are more coming in front of my eyes. So, so apologies for all the questions we couldn't answer. And thank you again, Roger.
All right. See you.
Bye-bye.